Hello students, today I'm going to explain this Green's theorem. The statement of this theorem is if C is any simple, smooth or piecewise smooth closed curve bounding the region R, and inside that region R, f, the function f, the function g and their first order partial derivatives are continuous, then the line integral over the closed curve C f dx plus g dy will be equal to the surface integral curly g by curly x minus curly f by curly y dx dy, where the integration will be carried in anticlockwise direction of the curve C. Now what is the meaning of this simple, smooth, piecewise smooth closed curves? So simple curve means which do not cross or intersect itself. Like this curve is not intersecting itself, so it's a simple curve. It is intersecting itself here at this point, so it is not a simple curve. It is again not intersecting itself anywhere, so it is a simple curve, and again this is intersecting here at this point, so it is not a simple curve. So the curve which do not intersect itself is called what? The simple curve. Secondly, the closed curve. What is closed curve? A curve which has no open ends, that means which is not open-ended, or you can say if its initial points coincide with the final point. If you're starting with this and you're coming back to the same point, you are closing the curve. That means that is a closed curve. Here it is also closed curve. Every curve is a closed curve. There is no open end in any curve. And what do we mean by smooth curve? If it is possible to get an thorough derivative from the equation of curve, that curve is called a smooth curve. That's mathematical language. Or at every point a unique derivative exists. You can have a unique derivative at each point. In other language, we can say if I move my finger across the curve and if it is smooth, you are feeling the smoothness, that curve is smooth. Like here it is smooth, but it is not smooth. From this point to this point it is smooth, but it has sharp corners. So it is piecewise smooth. In pieces, this piece is smooth, this piece is smooth, this piece is smooth, but overall it is piecewise smooth. Overall it is not smooth. In pieces it is smooth. So simple, which do not intersect itself; closed, which have no open ends; smooth, at which will get a unique derivative at each point, or you can feel the smoothness by moving the finger across. So by the definition, if C is a simple, smooth, piecewise smooth closed curve bounding the region R, and f and g and their first order partial derivatives are continuous in that region R, then this line diagram will be equal to this surface integral. So let us verify the result, the Green's theorem. So verify the Green's theorem for this integral, where C is what? The boundary of the region enclosed by this parabola. It is a right-handed parabola, it is this, and the line x equals 3 is this. If you see that this curve is what? A simple, it is not intersecting itself anywhere. Secondly, it is also closed, it has no open end. Third, it is piecewise smooth. From this point to this point it is smooth, and A to B it is all smooth, and there are sharp corners. It is not overall smooth, but in pieces the AB piece and BOA piece both are smooth, so we can say it is piecewise smooth. So given curve is simple, piecewise smooth or closed curve. Also the values of f and g which are given to us and their partial derivatives all are polynomials, and we know that all the polynomials are continuous everywhere, so it will be continuous within this region R. So all the conditions of Green's theorem get satisfied. So now we have to verify whether this line integral is equal to that surface integral or not. Now we have to verify this result. So let us verify this result. Let us start with the left hand integral. This is left hand. This is the value of f given to us. It is value of g given to us. Now the given curve C is not smooth. It is piecewise smooth. So we have to separate the pieces. One piece is BOA, another piece is A to B. So there are two pieces BOA and A to B. BOA and A to B. I break the curve closed curve C into the pieces BOA and AB. Now on BOA, on this curve BOA, what is the value of x? X is y square by 4. X is y square by 4. And on solving this we will get as the point of intersections are 3 square root 12. This is 3 square root 12 and this is 3 minus square root 12. So y varies from minus square root 12 to 12. Why? Because we have to carry the integration in anti-clockwise direction. Anti-clockwise direction, so we have to move from this point to this point. So here value of y is square root 12 and here the value of y is minus square root 12. So let us scroll down it. Now x on the curve is y square by 4 and y is minus square root 12 to minus square root 12. Now we have to get the values of other. Now we have the value of x which is y square by 4 and this is the range of y. So I substituted the value of, now take the derivatives, dx become this, y square is 2y by 4 and it becomes 1 by 2y dy. Substitute this x dx, all values there in BOA. We get what? X value is y square by 4, substituted, y square is y square, 2, value of x is y square by 4, y value of dx is 1 by 2y dy, and x square, it is again y square by 4 whole square, and dy is dy. After solving, after multiplying, squaring, adding y square by 4, y square into y cube into y, after simplification we will get this, and after the integration, now it is an odd function. For odd function, if the limit is from negative to positive or positive to negative, the integral value is 0, and for even function it becomes twice from 0 onward. So I integrated this, substitute the limbs, we get this answer. It is the answer for BOA curve. Now let us find the answer for AB curve. Now on AB curve, this is your AB curve. On AB curve, value of x is 3 and if you take the derivative dx becomes 0. Y varies from this. So substitute dx 0, value of x 3 and integrate. So again it is an odd function from negative to positive will give you 0 answer. So it is the sum of those two results. So it is the final answer for line integral. So let us calculate the surface integral. Now substitute the value of curly g by curly x here. It is curly g by curly x and it is curly a by curly y. Substitute value, we get this. Now here we have to calculate the limit. So y varies from minus square root 12 to plus square root 12 and x varies from y square by 4 to 3. Substitute here, integrate this x. So after integration of x square by 2, substituting the limit, we get this. Again integrated this, we get the final answer this. So from both the answers are same, so hence the Green's theorem is verified.